I'm a lecturer in robotics at the University of Bristol and at the Bristol Robotics Lab. I'm very interested in swarm systems, so if you look at birds and ants, they can do these beautiful, complex patterns, and I'm interested in taking inspiration from these swarm systems and using them in real-world applications. So before I used to do swarms of flying robots, but now what I'm focusing on is on making swarms of nanoparticles for cancer applications. So if you look at nanoparticles are very good at going into tumors, and what I'm interested in doing is figuring out how trillions of these nanoparticles can work together as a collective, as a swarm, and hopefully to improve treatment outcome. What's interesting with these nanoparticles is that they have a number of very simple functionalities. So you can change their size, their shape, their charge, you can coat them with molecules, and you can load them with little drugs that they can release in a controlled fashion. And so that gives you a lot of knobs that you can turn on the design of these nanoparticles, and depending on how you design them, they're going to work together in different ways. But that's not very different from a normal treatment, right? If you were to inject a chemotherapy, those molecules would also interact with one another. So it's not that they're, very smart, or they're like the Internet of Things, or they're overly complicated. They're just a little bit more complicated than the simple molecules we're used to using for treatment. And we're trying to figure out how these simple things can work together in a more efficient way. So basically, like swarm systems, very simple agents, not too complicated, but trying to figure out how they should work as a group. So nanoparticles can't really say where they want to go. They can't say, I'm going to go left or right or straight. They basically get taken up by the body, and then it's the body that controls the way that they move. So if you inject them in the bloodstream, it's the bloodstream that's going to bring them to where they want to go. In tumors, the bloodstream, or the vessels, are very leaky, and so particles leak out into those tumor tissues. And in those tumor tissues, very often what you get is diffusion, so the particles move randomly. The way in which we can change where they go to make sure that they go and they hit those cancer cells is essentially we can make these particles sticky, or we can decorate them with little molecules, and these little molecules allow them to go and stick to the cancer cells. And so essentially you can imagine these particles moving randomly in your tumor environment, but then they can go and stick to different tumor cells, and so that sort of changes their motion because they were moving, and now all of a sudden they're stopped, and then they might get eaten up by a cell. And likewise, you can have particles that bind to each other. So there are researchers that are looking at ways to make particles that self-assemble, for example. So if you have particles that are very fast, if they self-assemble, they're going to become a little bit bigger, and it's going to be harder for them to move. So you can control them a little bit as well in terms of changing their size in that tumor environment, either by having them come together as self-assembly or break down as disassembly, and that changes their dynamics in the way that they move. There's also interesting systems that work using external energy, so systems that work based on magnetic fields, for example, where there you have a little bit more control in terms of where these nanoparticles work, but you're inputting that information from the outside world. So the beautiful thing with making very simple swarm systems, but that work in very large numbers, is that I think they have a number of applications in the real world. So for example, they could be used to clean up an oil spill, they could be used to deploy and do environmental monitoring, little sensors essentially that would walk around, for example, a forest to see if there's a fire. And the tricky thing is what you'd want is for these robots to be very cheap, very easy to deploy, potentially disposable, so things that would degrade or that you could leave in the environment and they would just get rid of naturally. And what that will require is swarm algorithms that are very, very robust to very noisy robots that don't work the way a perfect robot would typically work like in the lab. And I think by studying these nanoparticles and how nanoparticles work together, because they work in these complex environments and because they're so simple, I think we're going to design algorithms for robotic systems as well that have the potential to work in outdoor environments with very simple and noisy robots.
No deposit, no return.
No, well, we'll see, yeah. I have to think about the materials for those ones, but It's already helpful today to understand how trillions of nanoparticles or drugs work together in a tumor. They don't need to be swarming or doing anything intelligent, but just understanding how they distribute throughout a tumor tissue is already helpful for bioengineers now. So I think those models and that understanding of group behavior is already usable, immediately. I think things that are a little bit more advanced in terms of really making particles that cooperate, that have these beautiful emergent behaviors, that's going to take more time. And part of it is that we need to test these in the lab at the nanoscale and understand how they work and what the material should be. And the other part is whatever we develop, if our goal is to be in a biomedical setting, they will need to go through the normal FDA approval and hit all the different requirements and test for toxicity, make sure that they're working in the way that we want them to work. And so we'll need to go through the normal pipelines to make sure that these are just like any other drug. For me, a swarm is a system where you have very simple agents which only have local information, so they can either talk to their neighbors or they can sense their local environment. So there's no leader in these swarms. And through these very simple interactions, they're able to achieve complex behaviors that are, that go beyond what the individuals could do. It's been great. So I had been following Austrian robotics for quite a bit, so it's interesting to be here and actually see the people that I've been interacting with on social media. And it's beautiful. It's really a beautiful setting here. You can see there's a park, there's the grass, the university is beautiful, and the talks have been great so far.
Thank you very much.